Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about rich regression, a popular technique that uses regularization to mitigate overfitting in linear regression. First, we're going to see how effective rich regression can be on real data, and then we're going to try to understand why it is so effective. Let's get to it. We're going to talk about rich regression. The regression problem is the problem of estimating a quantity of interest that we typically call the response from multiple other quantities that we call features or covariates. In our previous video on linear minimum mean squared error estimation, we saw that if we model the response as a random variable y and the features as a random vector x, where each entry corresponds to one feature, then the optimal linear estimator of the response given the features is of this form. First, we center the features using their mean. Then we apply linear coefficients that depend on the covariance matrix of the features and the cross covariance between the features and the response. And then we add back the mean of the response. Of course, in practice, we don't fit models to random variables, we fit models to real data. When we want to fit models to data, we have a finite number of examples where each example corresponds to d features and the corresponding value of the response. We saw in our video on ordinary least squares that the optimal linear estimator of the response given the features, if we're using a finite data set, is of this form, where essentially we replace the covariance matrix of the features by their sample covariance matrix computed from the data. We replace the cross covariance between the features and the response by the sample cross covariance computed from the data. And then what we use to center is the sample mean of the features, and at the end we add back the sample mean of the response. This estimator minimizes the sum of squared errors over the training set. This is the training set, the data that we have available to fit the linear model. From now on, in order to make our life easier, and because it doesn't really matter that much, we're going to assume that everything is centered to begin with, so that we don't have to worry about centering the features or then uncentering, if you want, the response at the end. Okay, we're not going to have to worry about any additive constants. Now let's take a look at how ordinary least squares performs on a real data example. Here we're going to try to estimate the temperature in Versailles, Kentucky that's a response, from 133 other features that encode temperatures at other locations in the United States. When our training set is very large, this is why I wrote large N there, this is what the linear coefficients look like. Let me tell you a little bit more in detail what I'm plotting here. This is the location of the response. Okay, we're trying to estimate the temperature right there. And I have also plotted the linear coefficients in our linear regression model corresponding to each of the locations that correspond. I said correspond like 20 times in this sentence. Each of the locations assigned to each of the features. And when I plot that coefficient, essentially what I do is I plot a marker whose radius is proportional to the magnitude of the coefficients. So immediately we see that the biggest coefficients are the ones that correspond to locations that are closer to the response, which makes a lot of sense. Whereas coefficients for locations that are far away are much smaller. So this, we obtain a very reasonable model that performs a local weighted average of temperatures at locations that are close to the response. This happens when we have a lot of data, but let's take a look at what the coefficients look like when we have different amounts of training data. So here, the x-axis tells you the number of training data. This is what happens when we have a lot of training data. These are all the coefficients, so there's 133 lines here. Most of them are gray and they're quite small, and I've highlighted in bold the three coefficients corresponding to the three geographically meaningful locations, which are these three guys, that are close to the response. When we have a lot of data, the linear model makes a lot of sense. It basically just mostly uses locations that are close to the location of the response. When we don't have a lot of data, here when we're close to the number of features, the coefficients go bananas. This is a phenomenon that we studied in our video on coefficient error in linear regression, and we saw that it tends to correspond to, I'm using corresponding a lot in this video, I'm going to try to stop from now on, right there where the coefficients go bananas, okay, this part here on the left, we observe that the error, so here I'm plotting the test error in black and the training error in white, the training error goes to 0 there. It becomes very, very small because we're overfitting the data, the training set. Why do I say that we're overfitting? Because when we apply the model to held out test data, we have very large error. In the video on training error, we gained an understanding of why the training curve looks exactly like that. And in the video on test error, we understood why the test error behaves like that. But essentially, we have a problem when we have a small number of data. What happens is that large coefficients, large fluctuating coefficients that kind of cancel each other, manage to overfit the training data, resulting in a model that does not generalize to held out data and is therefore not very useful. How can we address this issue? Well, if you remember from the ordinary least squares video, the ordinary least squares estimator minimizes essentially the training error, okay, the sum of squared errors on our training set. Instead, what we can do is add a term to this cost function that promotes smaller coefficients. It tries to prevent the estimator from having coefficients that are too big. A very reasonable term to add is the sum of squared coefficients, because if we minimize this whole quantity where here we have the training, so we have a term that corresponds to the training error and then a term that corresponds to the sum of squared values of the coefficients. If we minimize this whole cost function, we're kind of telling the model, sure, fit the training set, but don't use coefficients that are too large, because we know that when you do that, we tend to overfit. This technique of augmenting cost functions to try to promote a certain structure in the coefficients is called regularization. Here we're penalizing the sum of squared coefficients. We will see in one of the following videos how we can use other penalties to promote other kinds of structures, in particular sparse structure. So here, the importance of the regularization term is governed by this regularization parameter lambda, which is a positive constant. If lambda is very small, then this term doesn't matter, and we're just minimizing the training error, and we end up with something like the ordinary least squares estimator, or very close to it. If lambda is too large, though, then this term won't matter anymore. We will just minimize this, and what's the best way of minimizing the sum of squared coefficients? Setting them all to 0. What we hope is that in between, for intermediate values of lambda, we manage to fit the training data without having large coefficients that overfit. Let's take a look in our example. Here I'm looking at a situation where I have 200 data points. Remember that the number of features is equal to 133. So this is, we're in the small data regime. We don't have a lot of training data. And here I'm showing you the 133 coefficients of a model fit via rich regression for different values of the regularization parameter. When the regularization parameter is very small, the coefficients go bananas, just like in ordinary least squares. This is not surprising because when lambda goes to 0, essentially we have the OLS estimator. This is problematic because these geographically meaningful coefficients are drowned by these other coefficients that are becoming large. These other coefficients in gray that are becoming large in order to overfit the training data. When the regularization parameter is very big, what happens? Everything goes to 0. Because the regularization term in the cost function dominates, and the best way of minimizing that is just setting the coefficients extremely small. In between, something interesting happens because the other coefficients become very small, but these coefficients that are geographically meaningful are quite large. That's the regime where the model is able to fit the training data reasonably well, but without all the other coefficients becoming large. And we hope that that is going to be a good model. We'll take a look at its training and test error a little bit later. But first, let's think about how we should choose lambda. By a little bit later, I mean almost right now. Should we choose lambda? Do you think we should choose the lambda that gives us the best training error? Well, no, right? Because the best training error is going to be achieved by just ignoring the regularization term, which is achieved by setting lambda to 0 and obtaining the OLS solution. We can see this very clearly when we look at the training error. Here it is. When the regularization parameter is very small, we obtain the best training error. This is not surprising because we obtain the best fit to the training data, but we're overfitting. How do we see that? Because when we look at held out test error, the held out test error is larger than in this intermediate regime, which is precisely where we see some very reasonable coefficients. Then, of course, when we set everything to 0, both the test error and the training error are really bad. We're severely underfitting because we're just setting all the linear coefficients to 0. How can we find the point where we're doing well on held out data? The answer is very simple. We use held out data. You take your training set and you separate it into a subset that you're going to use to fit the model and a held out subset, which we call a validation subset, which we're going to use to decide on the best lambda regularization parameter. That's called validation. You can also do multiple subsets, and that's called cross-validation. We're not going to get into the details, but you always need to do this when you use regularization techniques to mitigate overfitting. So finally, if we do this for all the values of n, these are the OLS coefficients. This is just the same plot that we saw earlier, where when we have a lot of data, we're doing very well. When we don't have a lot of data, boom, the coefficients go bananas and we overfit. If we use validation to choose the best regularization parameter for each value of the training data, these are the coefficients that we observe. So the non-geographically meaningful coefficients stay small thanks to the regularization parameter, and we're able to essentially find a model that uses the geographically meaningful coefficients mostly, and therefore we can expect it to generalize better to held out data. Notice that here when we have a lot of data, that doesn't matter. I should have pointed that out a bit more clearly. Here is where it matters. I mean, here is the huge difference. Does this result in better held out performance? It definitely does. I'm showing you here the training error of OLS and of rich regression. We see that here in the regime where we don't have a lot of data, we get more training error with rich regression. Why? Because we're not overfitting. When we look at the test error of both models, boom, rich regression has much better test error because it is not overfitting the training set, and it's able to identify the important coefficients and put more weight on the important coefficients, obtaining a better model. So in summary, rich regression in this example and in many other situations works very well for real data. Now we're going to try to understand why that is the case. And we're going to do this in 3 steps. First, this is the plan. First, we're going to derive the relationship between the ordinary least squares and the rich regression coefficients. Then we're going to work through a simple example that is going to show us why rich regression is very effective using a linear response with additive noise. We're going to assume that the response is actually linear and that we have some additive noise, and that is going to allow us to understand the mechanism that rich regression uses to mitigate overfitting. And then finally, we're going to do a comparison between the bias and the variance of ordinary least squares and rich regression. Okay, let's go. So first, we're going to derive the relationship between the OLS and the rich regression coefficients. And in order to do that, it's going to be super useful to express the cost function of the of ordinary least squares in matrix vector form. So we're going to basically stack all of the response values into a vector that we call the response vector. We call it Y train because this is the training set that we're going to use to fit the linear regression model. And similarly, we're going to stack in the rows of what we call a design matrix, X train, we're going to stack the values of the features for the first example, the second example, and so on, down to the nth example. So here notice that we have D columns corresponding to each of the features. Great. Now, if we look at the rich regression function, we can express it as the matrix vector form of the OLS function that we just derived in terms of the response vector and the design matrix. And now we can be a bit sneaky and transform the sum of squared coefficients into something that also goes into an L2 norm. Or maybe I should have said here that this sum of squares, back here, I should have maybe said that this, maybe I'll show you also the design matrix, this sum of squares is just the definition of the squared L2 norm. The squared L2 norm is just the sum of squared entries of the vector that you're applying this norm to. So going back to the rich regression cost function, we have a first term that is exactly the same as the OLS cost function, and then we have this additional term, which is the sum of squared coefficients. So it's the squared L2 norm of the coefficients. We're gonna write a matrix, an identity matrix there, which doesn't change the vector. You will see why in a moment. And we're going to put the regularization parameter into the squared L2 norm, so that's why we have to take a square root. Why do we do all of this funny business? Because now we can write this as follows. We can write it as a new response vector minus a new design matrix that hits the same linear coefficients. And this is great because this looks like the OLS cost function. First, maybe let me tell you quickly why this is equal to that, or because when you do the squared L2 norm of the coefficients, if you have like if you do the squared L2 norm of a vector that has, I don't know, not x is a bad example. So here we have like maybe a vector A and a vector B, and we have the L2 norm. This is actually equal to the L2 norm squared of A, L2 norm squared of course, plus the L2 norm squared of B. So you can check that that is true. So now here, that's why these two expressions are the same. Notice that Y train is going to be like what we're going to subtract from Y train is the design matrix times the linear coefficients. And what we're going to subtract from 0, which is this same 0. Oh, I should have said this 0 is actually a vector that has these zeros. Okay, in case you were you were wondering why on earth are we subtracting a vector of coefficients from a single number. No, that's a vector of these zeros. That vector of these zeros, we're subtracting the square root of lambda I times the coefficient. So it's exactly this expression. Okay, you can check on your own, but if you accept that, now we have an OLS problem with this modified response vector and this modified design matrix. Why is this very useful? Because we know the closed form solution to the OLS coefficients. So we're going to apply that to obtain the closed form of the rich regression coefficients. So this is equivalent to the OLS cost function with this new design matrix and this new response vector. Now, if you remember when we derived the OLS, the ordinary least squares estimator, we did it in terms of the sample covariance of the features and the sample cross covariance of the features and the response. Now we're going to write both the sample covariance and the sample cross covariance in terms of the feature vector and the design matrix, so that then we can apply the resulting expression to our rich regression problem. What is the sample covariance matrix of the features in terms of the design matrix? By definition, the sample covariance matrix looks like that. If you do this product of the design matrix, because this guy contains, if you remember, the features as its rows, okay, this guy is going to, like if you transpose it, you have the features as the columns. So when you do this outer product, you obtain exactly that, okay? So we have that the sample covariance matrix is 1 over n minus 1 times this product of the design matrix with its transpose. Very similarly, if we look at the sample cross covariance between the features and the response, because this guy now is of this form, the transpose of the covariance matrix looks like that. If it hits the response vector, we get exactly this expression, and then we have to divide by n minus 1. So now we're going to just plug this in to our closed form for the OLS coefficients, and this is what we get. You might be wondering where the n minus 1 went. Here we have an inverse. So this would be times n minus 1. The n minus 1 could come out of the inverse multiplying. And here we would also divide by n minus 1. So this cancels out. Excellent. We have obtained an expression for the OLS estimator in terms of the design matrix of the features and the response vector. Now we're going to go ahead and apply this expression to our rich regression estimator, which we can write as an OLS problem, as we saw a couple of slides ago, in terms of this modified response and this modified design matrix. This is going to be the minimum of that optimization problem. This comes from the fact that that's the minimum of the OLS cost function, as we discussed in the ordinary least squares video. Oops, I almost dropped my eye pencil, but I didn't, luckily. Now what we're going to do is we're going to plug in back the design matrix and here it is, the modified response vector. So when we compute out this product, we have the transpose of the design matrix times itself, and then we have this identity times itself. That is going to be equal to this, or maybe I should have done it like that. This equal to that times that, and the two identity matrix give us an identity matrix times lambda, all inside that inverse. This is much easier. The transpose of the design matrix hits the response vector, and this identity matrix just hits 0, so it disappears. That's why only this guy remains. And just like that, we have a closed form solution for our rich regression coefficients that we can then study. If we go back to the sample covariance matrix and the sample cross covariance, we remember that the sample cross covariance is this guy divided by n minus 1, and the sample covariance matrix is this guy divided by n minus 1. So here we can multiply by n minus 1 and divide by n minus 1, and then put the n minus 1 inside the inverse, and there it's going to divide, right? So this is where this guy comes from. Awesome. So we have an expression for our rich regression coefficients, and we see that they're very similar to the OLS coefficients, except that we're adding a matrix to the sample covariance matrix of the features that is the identity times lambda. So we're kind of adding to the diagonal of the sample cross covariance matrix, and then we take the inverse and we apply to the cross covariance, just like in OLS. Now, in order to gain a little bit more of an understanding of how both ordinary least squares and rich regression operate, we're going to remind ourselves of the principal component analysis perspective on the features. If you don't remember principal component analysis, we have a whole video about that. Go take a look. What we do in principal component analysis is we take an eigendecomposition of the, in this case, sample covariance matrix of the features that gives us this matrix U. I'm going to show you this matrix U that contains the principal directions of the features, this diagonal matrix big lambda that contains the variance, the sample variance of the features in those directions of space, and then we have the transpose principal directions. Remember that if we order these guys so that this is largest and this is smallest, the features have the most sample variance in the direction of U1, which is a unit norm, L2 norm vector, and that variance is this value. If you go look at the PCA video, you will realize that we used lambda for that value in that video because we used big lambda for this matrix. But here we don't want to confuse this with the regularization parameter of rich regression. So that's why I have changed the notation to this xi, I think it's called xi letter. Okay, so in the directions orthogonal to the first principal direction, the largest sample variance is achieved at U2, at the second principal direction. At that sample variance is equal to xi2, and so on and so forth until we reach the last principal direction, and this is the direction of least variance of the features. Again, please review the principal component analysis video if you don't remember this stuff. In the OLS video, as I have mentioned before, we saw that the OLS coefficients, and I've mentioned it several times in this video, the OLS coefficients can be written as the inverse of the covariance matrix, the sample covariance matrix times the sample cross covariance. If now we write this, and maybe here I'll give you some more details. So the sample cross covariance is of this form. Remember that if you have the inverse of two matrices, the product of two matrices A, B, is equal to the inverse of B times the inverse of A. So this inverse is equal to the inverse of U transpose times the inverse of this diagonal matrix times the inverse of U. But these guys are orthonormal vectors. Because of that, U transpose is the inverse of U. Or rather, the inverse of U transpose is U, is what I meant. We have the inverse of lambda, and then we have U transpose. You might have noticed that I spaced out a bit like there for a moment. It's because I was wondering if this is a squared matrix, but it is, right? Because we have the principal directions and each of them have the entries. Okay, it's, yeah, I spaced out. Sorry about that. Okay, so now we have this expression for the inverse of the sample covariance matrix. This can actually be written as the each of the columns of this guy times the corresponding entry of the diagonal of this guy times each of the rows of this guy. So we can write it as j from 1 to d of uj times the entry, the corresponding entry of this guy, which is 1 over xij times uj transpose. And that's where this comes from. All right, and that hits the cross covariance. Now, notice, I was going to say remember, but there's no reason why you would have to, I haven't said that yet. This is the principal direction vector, and the rest is a single number. That single number is the value of the coefficient of the OLS coefficient. So it's the amplitude of the OLS coefficients in the jth principal direction. We're doing a change of basis. Here we typically think of the OLS coefficient expressed in the standard basis. If we do a change of basis to this basis because they're all orthonormal vectors, then the amplitude in each of the amplitude multiplying each of those vectors in this change of basis can be understood as the amplitude of the OLS coefficients in that direction are equal to an inner product between the principal direction and the cross covariance divided by the sample variance of the training data in that direction. And this is exactly why, and we talked a lot about this in the video on coefficient error, when we have a small sample variance in a certain direction of the feature space, that's where the coefficients explode. Realize that here if xij is very small, boom, the coefficient is going to become very large. We will see an example of this in our second part of our plan when we look at the simple example. From now on, I'm often going to express the regularization parameter as lambda sub n, because you will see that it tends to be divided by n minus 1, and I just wanted to simplify notation. So when we look at the rich regression coefficients, it's going to be useful to realize that if I take, remember that this is what we're taking the inverse of when we're computing the rich regression coefficients. If I'm adding this sample covariance matrix to the identity and I ask myself, what is the eigendecomposition of this? There's a very useful trick. You have to remember that for any orthogonal matrix that is formed of orthonormal columns, I can always write the identity like that. So I can choose the one that contains the principal directions of the sample covariance matrix of our features to make my life easy. And if I do that, then basically this is just, I can put this together with the identity, which we can imagine is there in the middle, to obtain this expression, where now these are still the principal directions of this whole matrix, and the eigenvalues in between, the diagonal eigenvalue matrix in between has been modified to add lambda sub n to each of the eigenvalues. When we take the inverse of this, we're going to have, remember, the inverse of this guy, which is just u, the inverse of this guy, which is this guy, and the inverse of u, which is u transpose. Because of this business that the inverse of A times B is equal to the inverse of B times the inverse of A. Now, by the same argument that I used before, where you can express this product as the first column times the first entry of the diagonal of this guy times the first row of this guy plus the second column of this guy times the second entry in the diagonal of this guy times the second row of this guy. So this is exactly the same as what we did, just to be very clear. This is exactly the same thing that we did here. By that argument, we can express this inverse like that, which is very useful because, as we had derived, that inverse is what hits the sample cross covariance between the features and the response to give us the ridge regression coefficients. So now we have again the ridge regression coefficients in terms of these vectors that are the principal directions of the features, okay, of the features in the training set. The coefficient now is very similar to the coefficient. So just to be clear, these are the features, these are the principal directions, which means that this is how the amplitude of the ridge regression coefficients in that direction look like. And they are very similar to the OLS coefficients, except that we're adding lambda here, which is pretty cool because now if psi j is very small, if lambda is not so small, it's going to prevent the coefficient from exploding. And that's the whole point of why ridge regression is able to mitigate overfitting, as we will see in much more detail in a moment. We can express, this is going to be very useful, we can express the ridge regression coefficient and the amplitude of the ridge regression coefficients in every principal direction of the features, because they look very similar to this. This is the expression we derived for OLS, for ordinary least squares, and this is the expression we derived for ridge regression. We just need to multiply and divide by this guy, and multiply and divide by this guy, and now we have the OLS amplitudes times this term, where if we bring this guy down, we just have the OLS coefficients divided by a certain value. This means that ridge regression takes the OLS coefficients, and if we put them in the basis of the principal directions of the features, all it's doing is shrinking the OLS coefficients, and the cool part is that it shrinks them differently depending on the sample variance of the features in that principal direction. And this is crucial because, as we will see in a moment, it shrinks them in exactly the right way. Let's see what I mean by that. Thank you for your patience, by the way, with all of these derivations, but I needed to do them to show you that ridge regression shrinks the OLS coefficients. So what do I mean by it shrinks them in the right way? So we have just seen that this is the shrinkage factor of OLS. Now imagine that there's just two principal directions, and in the first one, the sample variance is very large, and in the second one, the sample variance is very small. Then we can find, then the ridge regression coefficients are going to look like that as a function of the OLS coefficients. And if we manage to find a lambda such that lambda divided by xi1 is very small and lambda divided by xi2 is large, which should be possible, right? Because xi1 is very large, so 1 over xi1 is small, and xi2 is small, so 1 over xi2 is large. So it should be possible to find such a lambda. Then the first coefficient, because this guy is very small, so it doesn't count, essentially stays the same. And the second coefficient, because this guy is so large, is squashed. Boom, it becomes 0. This is great because when the sample variance is small, is precisely where the coefficients explode and go bananas, and there's this noise amplification that we talked about so much in the video on coefficient error. And those coefficients are precisely the ones that are going to be suppressed by ridge regression. To make this much, much more precise, we're going to take a look at a simple example where we know that the response is linear, but there is additive noise that can get amplified if what I just said happens. Okay, so we're going to look at this example where we have a fixed design matrix and a fixed noise vector, and there are these true coefficients so that the response is actually connected. It's a function of the features, a linear function of the features with this fixed true coefficients. But there's this additive noise, and we're going to assume that everything is centered to have zero mean, just so that we don't have to worry about the additive constants in the linear model. We already derived under these conditions in the video on coefficient error that the OLS coefficients under these assumptions are equal to the true coefficients times a term that depends on the inverse sample covariance matrix of the features and the cross covariance between the noise and the features. And if you remember, this is the problematic term because in the limit where we have a lot of training data, that essentially becomes zero if the noise is uncorrelated with the features, which it should be, because otherwise it should be part of the features if it's not uncorrelated. But with finite data, it's not going to be exactly zero, and then it can explode because of the inverse sample covariance matrix if we have collinearity. All of this is much better explained in the video on coefficient error. This is what the cross covariance between the noise and the features looks like. In this example, we do have collinearity. Realize that the first entry of the 4 examples of the features that we have here are very similar to the second entry. So then hence we're going to have collinearity. These are the value of the true coefficients. We add this noise to our data, and that gives us our response. So here we have just 4 data points, 2 features. These are the true coefficients. You see them there. Now we're going to do a change of basis to look at them in the basis of principal directions of the features. So first we take an eigendecomposition of this design matrix that I'm not showing you to find the 2 principal directions. And now we do a change of basis to express the true coefficients in this basis of principal directions, okay? This is the first principal direction, second principal direction. We want to find these guys. How do we do that? We just take inner products because these are orthonormal vectors with the true vectors. And this is the amplitude of the true coefficients in the first principal direction. This is the amplitude of the true coefficients in the second principal direction. We will see that this allows us to understand why OLS fails and why ridge regression can prevent it from failing. Okay, so if we take this principal analysis perspective, the OLS coefficients are equal to this. This we already derived in a previous video. So if we express them in terms of the, here we're expressing the true coefficients in terms of the principal directions, and here we're doing this decomposition of this guy into U lambda minus 1 U transpose, which is then equal to this sum, if you remember. We've done this a couple of times, so I won't repeat it. This means that if we put all of this together, okay, we just to highlight, here we have the jth principal direction in both terms so that we can just take it out. And this is the amplitude in that jth principal direction of the OLS coefficients. And what we observe is that the OLS coefficients are equal to the true coefficients, good news, plus this term that, as I mentioned, is going to depend on the sample cross covariance between the features and the noise. The good news is that that sample cross covariance is very small, because when I generated this data, I generated from a model where the noise is independent from the features, as it should be. Like, that kind of makes sense, because otherwise it would be part of the features, so that's very small. But because the features are collinear, we have very, very little variance in the second principal direction, which I'm going to highlight here. And that is going to make that part of the OLS coefficients explode. The amplitude of the OLS coefficients in the second principal direction is crazy. And it's going to completely distort the OLS coefficients. This is the same phenomenon that we talked about in the video on coefficient error in linear regression. So now, when we look at the ridge regression coefficients, we see that we see that we derived this expression where they're equal to the OLS coefficients. This expression holds all the time, right? Now we're going to see what happens, for our specific example, but this expression that we derived earlier always holds. So if we look at the amplitude of the ridge regression coefficients in the first principal direction, it's exactly equal to this. And if we look at its amplitude in the second principal direction, it's exactly equal to that. Okay, I'm going a little bit crazy with the arrows, but hopefully it's clear. And remember that we have this term that is super important. Now for our example, I'm just going to replace the two sample variances by their actual values. And these are going to be the values of our ridge regression coefficients. Remember that this guy was equal to the true coefficients minus, I'm going to minus this, right? Minus 0.03 and plus 2.03 below, just so that you see where that comes from. So I'm going to just plug that in. And this is our expression for the first ridge regression coefficient, which is equal to the OLS coefficient divided by that term. Second ridge regression coefficient divided by that term. Here is where it becomes really important that the shrinkage factor that we see here in the denominator is different for both ridge regression coefficients. Here, lambda is multiplied by 0.03. I'm going to show you this on a graph because lambda is multiplied by 0.03. This is the first ridge regression coefficient. It becomes smaller later, whereas the second ridge regression coefficient, where lambda is multiplied by 1,000, becomes smaller much earlier. It's this guy. Why is this important? Well, let's take a look at this carefully. Again, this is the expression for the ridge regression coefficients, the amplitudes of the ridge regression coefficients in both principal directions for different values of lambda n, of the regularization parameter. When the regularization parameter is very small, here we see that the amplitude in the direction of the first principal direction is exactly right. Why? Because here noise amplification does not happen because the sample variance of the features in that direction is not very large. But in the other direction, this is completely bananas, okay, as we saw, because there's very little sample variance in that direction, there's this crazy noise amplification that completely distorts that amplitude of the OLS coefficients. And here, the ridge regression coefficients are equal to the OLS coefficients because lambda is so small. As lambda becomes big, it starts shrinking both amplitudes, but because it shrinks them in a way that depends on the sample variance in each direction, when the sample variance in that direction is smaller, it shrinks it much earlier. So this shrinkage occurs much earlier, whereas for a certain time, at least, not a certain time, for some values of the regularization parameter, the first amplitude remains essentially the same. This is great because at this point, this is 0. Okay, I'm going to erase stuff so that this point is clear because this point is super important. So again, we start with a good first amplitude and a horrible second amplitude, completely distorted by noise amplification. Now, because the sample variance in that direction is smaller, ridge regression starts shrinking that, but it leaves the other coefficient, the other amplitude alone, because the sample variance in that amplitude in that direction is much larger. This allows us to reach a point here where we have squashed this extremely noisy second amplitude and we preserve the good one, the one that is not as distorted by the noise. Of course, if we continue, then eventually that one is also going to be squashed and we're going to get 0 coefficients, which we know is what happens when the regularization parameter is too large. But we do have a sweet spot here where we're estimating the principal direction that we can hope to estimate because there is sample variance in the features in that direction. The other one, there is no sample variance. Okay, so hopefully that made sense. This is the magic of ridge regression. If we look at the ridge regression coefficients in this other standard basis, in the normal standard basis. These are the amplitude of the first entry and the second entry of the ridge regression coefficients. We don't really understand what's happening. We see that here they have gone bananas. Why? Because the amplitude in the second principal direction is amplified, has amplified the noise dramatically. Here we see that the values seem a bit more reasonable, and eventually they go to zero. But of course, we don't understand it in the same way as when we look at it in terms of the principal directions of the features. There it's very clear that what is happening is that there's this shrinkage that is applied in each of the principal directions. And because the shrinkage is different and depends on the sample variance, that allows the estimator to squash the bad directions, if you want, and preserve the good directions, at least in this intermediate regime. Let me show you how the OLS cost function looks like for this example. Because of the collinearity, that's why it's so stretched in that direction, and that's why, and it's kind of flat in this direction, so the noise can bring the minimum very far in that direction. This is the bad direction. Okay, and this is the good direction, where the OLS solution is not going to stray very far from the true solution. Okay, I mean in this direction, in the orange, maybe I'll change the colors. So in the red direction, we're going to have a lot of error because there's not a lot of sample variance of the features in that direction. In this direction, we're going to have much less error. This is what the regularization term of the cost function looks like for lambda n equal to 0.01, which, just to mention, is within this sweet spot. And what this does is it distorts. Okay, so this is the OLS cost function. When we add this regularization term, it distorts the cost function to bring the ridge regression coefficients much closer to the true coefficients. Maybe I should have made clear that these are the true coefficients. Here you see a lot of error between the OLS coefficients and the true coefficients. When we add the regularization term, it distorts the cost function to bring the ridge regression coefficients closer to the true coefficients. And as we saw, it does it mostly by squashing this amplitude of the OLS coefficients. So here I'm expressing the OLS coefficients in terms of their amplitude in this bad principal direction, the second principal direction, and the first principal direction. And what ridge regression does is it squashes that principal direction and just preserves the one that doesn't have as much error. Okay, this is like a visual interpretation of what I was telling you before. And because of that, it's much closer to the true coefficients. And that's how ridge regression prevents overfitting. I've shown you just a single example, but now I want to give you an idea of how this works in general. And a good way of doing that is by deriving the bias and variance of ridge regression and comparing them with the bias and variance of ordinary least squares. In order to do that, we're going to again assume that we have this linear response which depends linearly on these n features that we're going to fix. So we're going to have these n feature vectors that are hitting a true vector of coefficients, but now for each of the data points, we're going to add random noise. Okay, these are going to be IID entries of random noise with variance sigma squared, and that is going to give us n random entries of the response, which are all, linearly related to the features through these true coefficients. And now we can ask, on average, how close is OLS to the true coefficients? How close are the OLS coefficients to the true coefficients? How close are the ridge regression coefficients to the true coefficients? We're going to center everything to have zero mean, again, so that we don't have to worry about additive constant in our linear regression models. These are the features. First, I'm going to show you what happens empirically. We just do some experiments where we fix these n collinear features. There are 8 of them, and we we basically sample the noise and solve for the 8 OLS coefficients, and we do this 100 times. Because I'm sampling the noise differently each time, I get a different coefficient each time. And what I see is that, in general, the coefficients are centered at the true coefficients, which are this star, but there's a lot of variance in this direction. Why is there a lot of variance in this direction? Because that's precisely the direction in which the features have very little sample variance, whereas in this other direction where they have more sample variance, the variance of the coefficients is much smaller. This is exactly what we talked about in the video on coefficient error, where we saw that the OLS coefficients are unbiased. This is why we see that the center of this cloud of points is exactly at the true coefficients. They are unbiased, but they can have large variance in directions where the features have low variance. Now, if we look at the ridge regression coefficients, if lambda is very small, essentially we see the same as for the OLS coefficients, no surprise there. But when we start increasing lambda, we see something very interesting. One, this is not unbiased anymore. The center is actually off, okay? And two, there is much less variance in the direction of, in this problematic direction where the features have small sample variance, and that's great because in general we have a much better estimator of the true coefficients, even though it's biased. Of course, if lambda is too large, the bias towards 0 becomes very large and the estimator is not that great anymore. Realize that the variance has become even smaller. Okay, so let's try to understand these empirical observations, which are that, unlike the ordinary least squares, ridge regression estimates are not centered at the true coefficients, so they're biased. And as lambda increases, the variance decreases faster in directions of low feature variance. So realize that the decrease in variance here is actually very dramatic in this direction, not so dramatic in this direction. Okay, as you can see there. Okay, so let's try to understand this. If we look at the jth principal direction of the features, the true coefficients can be expressed as the inner product between the principal direction and the true coefficients. This is the amplitude in the jth principal direction. We know, well, the OLS coefficients can be expressed as the amplitude of the OLS coefficients in that direction is also the inner product of that principal direction with the OLS coefficients. So that if we take the mean of the amplitude of the OLS coefficients in that direction, then by linearity of expectation, this guy can come out from the expectation operator, and here we get the mean of the OLS coefficients, which we proved in the video on coefficient error is equal to the true coefficients under our assumptions when the noise is independent and the response is a linear function of the features. So this means that the amplitude in every principal direction on average is the correct one, which is what we observed in our empirical observations. And when we go look at so this is for OLS, when we go look at the amplitude of the ridge regression coefficient in that direction, again, by linearity of expectation, is just the inner product between that principal direction and the mean of the ridge regression coefficients. We know that the ridge regression coefficients are equal to the OLS coefficients divided by these shrinking factors in each of the principal directions. This is why it's crucial to do this analysis separately in each principal direction. Otherwise, you wouldn't be able to do this. Now this comes out, and we have again the mean of the OLS coefficients, which we know is the true coefficients, divided by our shrinkage factor. So we see that the larger lambda is, the more bias the ridge regression coefficients are going to have towards 0, which is exactly what we see in our simulations. Okay, so there's the true coefficient and there's shrinkage towards 0. There's a bias towards 0 of the ridge regression coefficients as we increase lambda. Thanks to this formula So all hinges on this formula that we derived in our first part of the plan that connects the OLS coefficients with the ridge regression coefficients. So that was painful, but at least, in my opinion, it was worth it. Okay, now let's take a look at the variance. So the variance of the OLS coefficients in the jth direction is equal to this. This is something we derived in our video on coefficient error. And the critical part here is that we have 1 over the sample variance of the features in that direction. So in directions where we have small sample variance, boom, the variance of the OLS coefficient explodes. So if we look at the variance of the ridge regression coefficients, because we can express the amplitude of the ridge regression coefficient in the jth direction in this way, which is with what we derived in the first step of our plan, now this guy is going to come out because it's just a constant. It has to come out squared. And we have the variance of the OLS coefficients divided by the shrinkage factor, which depends on the sample variance of the features in that direction, and that is critical because it depends on it in exactly the right way. To show you what I mean, I'm going to show you the effect of this selective shrinkage for a specific example where we have these two coefficients. Okay, yes, for a specific example where we have just two coefficients, two features. For one, the sample variance is very large, and for the other, the sample variance is very small. We know that the OLS coefficients are unbiased, and in the direction where the, by now I should know this by heart, but in the direction where the sample variance of the features is large, then the variance of the OLS coefficient is going to be small. That's great. We are estimating well in that direction. In the other direction, where xi2, where the sample variance of the features is small, boom, noise amplification, but large variance, bad estimate. Okay, so we have a problem there. Now, when we consider the ridge regression coefficients, we have proved that there is this bias when lambda becomes large. It's biasing towards 0. And we have derived this expression for the variance of the ridge regression coefficients. Now we're going to choose a lambda such that lambda divided, this is exactly what we did in our simple example, lambda divided by the sample variance in the first direction is small, which is possible because that sample variance is large. And we're going to pick a lambda that when divided by the sample variance in the second direction, it's very large, which is possible because this guy is small. That is great, because now let's see what happens to the bias of the first coefficient. This is small, so boom, nothing happens. It's very similar to the original coefficient. There's very little bias in the first principal direction. What happens to the bias in the second principal direction? This is going to be very large. This is going to be negligible. It's going to kill this guy. Okay, so this is going to be more or less here. It's going to squash it. So this is kind of bad because we're introducing bias in the second principal direction. But remember that in that principal direction, the variance of the OLS coefficients is very large. So we're just looking at garbage. So we better squash that garbage. Now let's look at the variance. Again, this guy is very small, so that is negligible. Very small. We're preserving small variance in the first principal direction where we don't have bias. That's great. So essentially, we're preserving that first principal direction on average. And now let's look at the variance in the second principal direction, which was highly problematic. Well, now this guy is large now. So what it's going to do is going to make this whole variance small. And that is great. We have solved our variance problem. What we have to pay a price, because nothing is for free. And our price is that we have introduced this bias in that direction, but we really don't care because the estimate in that direction is bad anyways. Okay, remember that the OLS estimator was something like this. So in this direction, whatever, we might as well introduce some bias in exchange for squashing the variance in that direction. So our theoretical analysis exactly explains what we were seeing in our empirical observations by introducing some bias. By introducing some bias in certain principal directions where the features have low sample variance, ridge regression is able to severely reduce the variance of the OLS estimator in those directions, which results in preventing overfitting because we're approximating the true coefficients much better. Okay, and that's all I got. What have we learned? We have learned that regularization prevents overfitting, and in particular, ridge regression achieves this by performing selective shrinkage of the OLS coefficients in their principal directions. If you don't do this analysis using PCA in the principal directions of the features, this is impossible to realize. And variance in directions of low feature variance is reduced, but the bias increases thanks to this selective shrinkage. And that is why in this sweet spot in the middle, where we're managing to squash the bad principal directions, ridge regression achieves a much better estimate of the true linear structure in the data. And that's all I got. Thank you very much.